that updated. And that. Okay. Okay, hello everyone. I'm going to probably go live on LinkedIn soon. That okay. Feel free to say hello in chat. Um, talk about if things are working. Okay, hello. Okay, that latency is fun. Okay, well, let's go ahead. Pause. Pause. Okay, check. Okay. Um, hello. Okay. Go ahead, jump live there. Okay. We doing good? Okay, no data. So, connection healthy. Healthy. Duration. Why we not? we're doing good. Um, I don't like this. Okay. 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 Grab shareable link. To hit YouTube. Post full. Okay. Yeah. It should be hard to tell. Data is going all fine. Huh. Okay. Data is flowing. Okay. Okay. Return to live. Okay. Give me a second. I'm just gonna post the YouTube link right here. If YouTube, or no, if LinkedIn Live is having issue, check the multicast on YouTube. There we go. Okay, we'll take that. Okay. So thank you everyone for joining. I'm trying to keep up with what's going on. But feel say the hi in the chat. We have people in people from YouTube saying hi from Switzerland and the Netherlands. So feel free to say hi in the chat. My LinkedIn live stream manager is not being terribly useful right now. I'll try to keep track of comments in LinkedIn, but that may be a little slow. Okay. So let's get started. Thank you for joining. So today we're going to be looking at Altera's new Agilex 5 FPGA, and specifically on how the FPGA AI Suite interacts or utilizes the AI optimized DSPs. I am FPGA Zealot, or also Andrew Wilson, and thank you for joining us. You can watch this stream on YouTube, Twitch, or LinkedIn, and I do post on X and LinkedIn if you want to keep up with kind of the post in between. So some disclaimers before we start. This is a sponsored live stream from Altera. I'm grateful for the opportunity of Altera to be able to explore their hardware and their software. I am not employed by Altera. I am not a field application engineer. I do not offer official support for these products. The content of this channel or stream is for informational purposes only, and all the opinions expressed are my own. So, as we go through, feel free to ask questions. I will try to respond as best as I can. And feel free to just introduce yourself. Talk about where you're from, your FPGA experience. Are you new to the Agilex FPGA family, or is this something you're planning on using in future projects or programs? Feel free to share some of that information in the chat. So we're going to be looking at specifically the Agilex 5, which Altera has started releasing. The Silicon, they do have some stage releases, so I'm not exactly sure which SKUs are currently available. We'll be looking at the E series today with the larger logical unit, or logical element, 656,000 version. But if you want to look at more information, feel free to go check the Agilex 5 website, where they go more through the features. You can look at the different SKUs and their releases. Oh, they're all 2022. Okay. And this is smaller than their Agilex 7 FPGA, but there are some interesting new features on the Agilex 5 that aren't present on the Agilex 7 FPGA. That mostly being the AI tensor block, which utilizes a new function within the DSP. And we're going to walk through that function in the DSP today. There's also other features. This is on the Intel 7 nanometer processing node, so you can get relatively better performance, speed, and power to older generation FPGAs. They do have high-speed SerDes going up to 28 gigabits per second, supporting up to PCIe Gen 4. The board we actually are looking at has two PCIe connections, so you potentially could do a PCI bridge, which is one of my pet projects I've been wanting to do for a long time. We also can support up to LPDDR5 memory interfaces, and there's 4 processors, 2 A55s and 2 A76s. Okay. So moving on. So here is the Agilex 5 modular development kit. You can find this listed on DigiKey and Mouser. I think it's a great price for getting a SOM with a carrier card. The SOM itself has 28 gigs of DDR off 3 banks, which can be utilized by the processor system or the FPGA. On the carrier card, you get full PCI, or 4 lanes of PCIe, 2 display ports, 2 HDMI, SFP, and FMC that has 8 transceiver lanes. So there's a lot of good utility on this carrier card. And if you want to, you can develop your own carrier card to try out different systems or peripherals. And so you can find this on their website. Most of the information here, the DigiKey Mouser ordering information, they are in stock and you can order them. And they also have the schematics. They have example designs. They have a user guide. I think they have a pretty good documentation for bringing up this board. We're not going to go through the board test system or some example designs today. The Agilex 5 board is much easier to set up in Quartus than the Agilex 7 board that I did last year. But we'll walk through a few different examples of that. Okay. So for the content for the stream today, it's probably going to be 45 minutes to an hour long. We're going to look at the new DSPs. We want to understand, do a deep dive into how they work and why this is a game changer to a traditional DSP approach. We're going to be able to simulate that and actually be able to process video frames or an image to see how the pipeline process works. After that, we're going to be looking at how we get the FPGA AI Suite working with the provided Docker image, and how we can look at how these DSPs are utilized differently in the Agilex 5 AI core versus the Agilex 7 AI core, which I think is pretty cool. After that, we'll do a more complex demo where we're using Python to send real data over TCP, and then do some YOLO v2 bounding boxes on the images, and be able to look at what live traffic is looking like in Utah right now. So to begin, we're going to look at the Agilex 5 AI optimized DSPs. They're also called tensor mode. And basically, the new functionality on these DSPs, along with your traditional functionality, we have a new function that allows us to take data inputs with a they don't have the side loading here, with coefficients, like 10 coefficients or dot product with 10 coefficients, and it allows you to do two different coefficient kernels at the same time on the same input. On the right, you can see kind of a basic example. We have a video, or we have an input image, and then one DSP is able to process the Sobel top and the Sobel right images. And we'll walk through how that works. So I wanted to understand more of how this works in the system. So if we look at the variable precision DSP user guide, we can figure out how to operate this at the native level. I don't expect many people to be using this at the native level unless they're trying to really get a high efficiency out of the system. Hopefully a lot of the existing IP will already leverage this tensor mode. So this is the image we had on the slide, but we want to go look at the operational mode for it. So for this, we're going to be looking at the tensor fixed point mode. Make this easy to read for everyone. So we're going to be looking at the tensor fixed point mode for the system. Let's go, actually, let's talk about the data flow. Okay, here. So this is the data flow for the DSP. This looks rather complex. So let's go look at how it looks like at the HDL level. So I'm going to pop over to the Quartus project real quick, and you'll see in our IP catalog, we have the native AI optimized DSP for the Agilex. And if we double click that, we are able to set up the system. And so like we said, we're going to look at the tensor fixed point, and we're going to be looking at these at this block here that has the various inputs for data, the side channel, and the outputs, the two outputs for each convolutional coefficient set. So that's the upper level block diagram, and this is what it's doing on the inside. And what we need to do to load the coefficients, we have to use these side channels with load BB1 or BB2, be able to load these registers here that store the coefficient data. So we have our 10 inputs, and we actually have 4 sets of coefficients operating on 2 at once. We also have the shared exponential data for if you do floating point. Now, this is how it's loaded in. So we'll walk through this a little bit. Okay. Sorry, there's trying to. So I have CocoaTB set up to start off this simulation. I will include the source for this and explanations for this in the coming weeks, so that if you want to follow along and do the same simulation, you can. So CocoaDB is going to bring up Quartus, or bring up QuestaSim. Here is our inputs for our DSP and our outputs. So we're going to add that to the wave. And then just to look at how we're supposed to load in the kernels, we're just going to run 1,000 nanoseconds. And this will let us set up the CocoaTB. And CocoaTB is just a Python wrapper around the QuestaSim simulation that allows us to assign values with Python, which is, super useful if you want to do some interactive test bench or demonstrations. So we're going to load Sobel kernels, and we're going to do a Sobel top and right. To kind of explain what that is, we can go to this demonstration here. Here is the top. It follows lines kind of going when it tries to identify edge detection using a basic 3x3 kernel. And then we're going to do Sobel right, which is going to be doing a different direction, but doing the same edge detection. Make sure we don't have any questions popping up. So we're going to need to load in the data. So what we have here is we have our input values, and then we have a clock edge. So we're going to basically bit bang the kernel into the DSP. And the process with which we're going to do that is listed here in this timing diagram. So we're going to set BB1 high, and then we're going to load in the coefficient with a column. So, for example, this is going to be column 2, coefficient 5. We're going to ignore the sign extension and the 10th value. So we're just going to be using 9 down to 1 for our 2 different kernels. So here's where we're going to, I do this one. So we're going to do this edge by edge, loading in this value. And then we're going to look at the waveform to see how this works. Okay, going back to our waveform, let's pop out. Actually, we can just look at it right here. So we're going to have basically, we're going to have 2 2s, 4 1s, 2 negative 2s, which is the FEs, and then 4 negative 1s, which is hexadecimal FF. Let's see. Can we see if we do this radix? You signed fixed. S. There we go. So we're loading the kernels to 2 negative 1 and 1 and through to the 2 different coefficients, and they're kind of interleaved. So it's kind of hard to see out in that picture. So we have successfully loaded the 2 kernels into the DSP. Now we're going to run for an additional time, and then we're going to load the image. Before we do that, let's go look at how the image is going to be loaded in the fixed mode. So here in the fixed mode, we can perfectly pipeline our image, and the data will appear 5 cycles later. So that's how this system is going to operate. So going back to our simulation, we're just going to use NumPy and OpenCV to load in an image. Here's our demonstration image. It's actually an AI generated traffic picture. We're going to resize it so it doesn't take a ton of simulation time to process. So here we're going to load it into the simulation. And basically, we're just going to be processing the image. We're going to ignore the edge detection or the edge conditions for now and just focus mostly on the content. We're just going to shift down one so I don't have to deal with sign extensions, signed or unsigned at the moment for that. And then we're going to read the output value for column 1, the output value for column 2, do some basic post-processing thresholding, and then we should be able to look at the image. So it's finished. We'll load a different image here so you can see the change. So there is our image. We're going to run this for a little bit longer so we can look at the image being processed. Okay, so here is our DSP image going from 1,000 nanoseconds to that can be 310,000 nanoseconds. And we can zoom in on the initial part of the input and see the delay of the DSP. So here's where the data first changes, and then 5 cycles later, we get the output value here. So we have a question from YouTube. How many DSPs does this use? Yes, this is just one DSP. Just one DSP to pipeline both Sobel top and Sobel left filters. And now we can do a quick change and load in a different image. Do the chat one. Okay, I gotta run this again. So we'll do the nature image. What was the DSP sim? I'll do DSP sim image. So we'll do a little image with sharper. Okay. We'll do this image. This will be easier to see kind of the edge detection. Run. In the bottom left, the timer going. Okay, it's finished. And now we can see the top and left Sobel filters for this design. So to kind of summarize what that is, we're using one DSP, a single DSP that's perfectly pipelined that can produce 2 outputs at the same time, and it's has enough I guess performance to be able to process up to 10 values, which for a basic video filter, which is 3x3, 9 values, you can do 2 basic video filters in one DSP. Before we move on to the next section, If you've joined us since we've had some time, I want to thank you for coming to this stream. We're looking at the Agilex 5. We're looking at the new AI optimized DSPs with the FPGA AI Suite, and I just want to thank again Altera for sponsoring the stream. And we're going to be looking next at using their FPGA AI Suite to be able to run full neural networks on the FPGA. Okay. Images. Okay, so if you haven't used FPGA AI Suite before, you can look at a lot of my previous videos and be able to see how it kind of works with the whole FPGA structure. We're going to try to speed through this real quick and do a quick demo of their ResNet design, and then look at more complex design. So we're going to be loading a model, a pre-trained model from their model zoo, the OpenVINO model zoo. And then using a pre-built bit stream, we're going to be able to load that model into the FPGA and use the FPGA fabric to be able to process the image results. What's a good image for that? I like this image right here. And we'll be looking at the resulting utilization of the DSPs between the Agilex 7 and the Agilex 5 to see how that change happens. Okay. So moving forward, we're going to be using the FPGA AI Suite design example guide to show how you can load in a model and be able to convert it for the system. Okay, so let's zoom this in. I guess that much. So we're here. We are in the AI Suite Docker container, and there's good Docker instructions. It's really easy to get up and running for being able to convert and do quantization on these models for the FPGA AI core in the Altera FPGAs. So we're just going to go through the whole process. I've already downloaded the model, so we're just going to run through the converter so you guys can see how long this takes for being able to look at different models. So we've generated XML files that are that we then now can process for our specific architecture. So going to models, public, ResNet, D32, we have an XML file. And now, because we've converted it, we now can compile the graph for a specific architecture. And we're going to be using the Agilex 5 performance architecture. And we just have to use this basic command and specify the Agilex 5 architecture. I have that command floating over here. Pull that up. So there's two compile modes. There's the benchmark mode for memory mapped, and then they have a streaming mode, which uses the no folding option. And it's really easy, really quick to build these two models. and it breaks it down to you. So here is the reported throughput of DDR. This is the required bandwidth. And then we can see that the Fmax for the Agilex 5 core is 350 megahertz, and the different frames per second that we can achieve at kind of different test points. But the overall frame per second performance is reported as 90. With if we were able to increase the clock speed, we'd be able to achieve better performance. Let's see if the streaming DLA compile, leave that there for a second so you can see it, is any different. And you can see the streaming is limited a little bit more, probably related. Report anything different on the DDR? DDR bandwidth is slightly different, so that must be potentially affecting the performance. 110, 8. Okay, yeah, it just seemed like the streaming's a little bit different. Okay. So now this has produced in the demo, or it's the model folder, or the demo folder. We have the ResNet performance binary and the no folding binary, which we're going to demonstrate on the hardware in just a few minutes. But before we do that, I want to show you the utilization difference between the Agilex 5 and the Agilex 7. So here is the Agilex 5 kind of utilization report, and it actually reports the usage of these tensor floating point units within the FPGA, and we're using 128 of them. As for the Agilex 7, we're using sum of 499s 9x9 instead, which is a dramatic increase in the use of DSPs. So this new function, it does dramatically reduce the DSP usage for their performance core. And I think we could probably look at different architectures depending on your network, or different differences from the performance architecture, to be able to utilize the Agilex 5 as best as possible, to be able to use it as a edge AI processing system. So I'm gonna go ahead and bring up the FPGA. We can go look at the FPGA real quick. Okay. So the FPGA is coming up, and we can watch on the terminal as Linux boots. As this boots, if you're joining us from the beginning of the live stream, we're about to set up the FPGA to run a basic ResNet with the FPGA AI Suite tools. And I just want to again mention that this stream is sponsored by Altera. They did provide the hardware, and this is a great opportunity to explore the new DSPs and to try to see how we can use this SoC, this Agilex 5 SoC, as a edge AI device. Okay, so we're now going to go to mobile Xterm and do split view. There we go. Do vertical split. Okay. Root. Okay. Y'all can see. So going back, loading the model. So we've copied over the binaries, we copied over sample images, and we copied over the example architecture. I can go into this and just show that for you. These are what we've brought over. I guess we could also look at the sample images. And then once we brought that over, we can run the different benchmarks, the memory map benchmark and the stream benchmark, and they provide the instructions to do that. I have those pre-copied over. We can look at those. Okay. Okay. So we're going to do UIO device restart, which is going to, the UIO drivers are used to interact with the Avalon IP cores inside the FPGA. And then we're going to do some environmental variables so that we can run the DLA benchmark. So this is going to use the memory map interface and try to see how fast that you can run this neural network on the actual hardware. Using this performance, we are able to achieve an Fmax of 8964. So if we go look at that, not that one. Oh, I messed up the view for that. Let me see. If we want to go to, which one was it? Let's go to the top one, I guess. Yeah, here we are. So we're comparing the 8964 with the 8964. So the DLA core, the architecture estimation matches the real hardware, and we could always push the hardware faster. So next we're going to look at the stream interface. And this is going to actually report data output. So going from here down to the streaming demonstration. We're going to run the provided utilities stream interface bash scripts. And if you want to know what these files are doing, you can look in Cordella work. There is, under the runtime, there is streaming, and you have the streaming interface app, which the C++ file is provided for you, and you can modify it, which is what we're going to do next. You also have the image streaming app here, which explains what they're doing when they set it up. And then if we want to look at the script that is going to be here, root to scripts. So this script is just running at a rate of 50, and this is just setting up the input parameters with the folding, non-folding bit, the architecture system. Okay. So go ahead and clear. We're going to run inference stream. Clear. And we're going to go to app. We're going to run the image stream. Okay, so it's ready to receive images, and now we can run the images. The IDs, I didn't set up the IDs, but those are each different, one of the 1000 classifications. And here, once it gets to 1000, it provides kind of a simple inference rate. But this is being not running at max speed. The software is providing some pauses to it. So once it gets to 1,000, we can look at what inference rate the streaming interface was able to achieve. I was supposed to report that. Where else? Yeah, here we go. We are able to do an inference rate of 24 frames per second. And I assume if we wanted to increase that rate, there are other methods that we can achieve what was outputted by the AI compiler tool. Okay. Let me go ahead and turn off the FPGA. I need to get it up and running for the next demo. Make sure it's booting up. So next for our stream, we're going to be looking at doing a Python live demo using a YOLO v2 model. This is using the YOLO v2 traffic model provided by the OpenVINO Zoo. Let me see if I can go paste that down. There we go. So this is the next network we're going to demonstrate, and we can go, it doesn't really describe much here, but using the YOLO v2 tiny vehicle detection, has a fixed image size, and then it has a fixed amount of boxes and kind of anchors that you use to reference to get the bounding boxes to look correct. But we have downloaded and compiled this image. So what we're going to do is now go back to this demo, and I want to show you compiling the traffic YOLO v2. Okay. So now we're just going to go up to our last compile command here, and we're just going to change test bin and the XML. Oh, the XML is not there at the moment. It's gonna be, we have to go to 1.32. Now I can get the XML. YOLO v2 tiny detection. Okay. So a little less throughput than the ResNet, but less demand on the DDR, which is interesting. This is has divided the subgraphs into CPU and FPGA, and we can look at how that's broken down. So first one we want to do is we want to look at the unsupported layer chain graph. So I'm going to pull up the VS Code, and we're going to look at this model real quick, the dot files coming out of it. So going into flowing 3.2, there's unsupported. So they have a very specific function here that they called region YOLO. And this can't be translated to a pre-built function in the FPGA, so we're gonna have to run that in the CPU. If there was a way we could, potentially add this layer to the FPGA, it would help out a lot. Let's see what other subgraphs. We can look at the overall subgraph that is running in the FPGA. Can I search for CPU on this one? No. Ooh, they got new visualizations. And I wonder where that YOLO, does it tell you? I don't see it there. So there are a lot of useful data that comes out of this compiling that can help you understand what's happening in your system. Okay, here we go. So we have the subgraph here that's using the FPGA and then the CPU. Here we go. We can see it. This is a combined one. The YOLO region. Okay. So go back here. We've been able to compile the system, and I'll show you the binary I already made for it. So we have a Y2 bench binary right here. And this is what we're going to load on to the FPGA. Okay. Next, I'm going to show you a little bit of how we got the Python to interact with the system. If you want to go more into detail how I got this Python system up and going, the previous streams will have last year with the Agilex 7 kind of described this in more detail. But I will write an article in a few weeks that digs down into more what I did to get it working. So the basic thing I did was I have all these dot images. So going back down to here is I created a shared memory space right here. Not very complicated. I created a shared memory space that C++ and Python could interact with. So basically the inference will write the data to the the results to the shared memory space. And then we can go poke at the Python real quick. Okay. In the Python, we interact with that same shared memory space. We also use the UI2 device to set up the video preprocessor, which is just the width and the height and the red, green, and blue shift. We also are using the OS semaphores to be able to communicate with C++ to be able to kind of lockstep between which when each inference finishes to provide additional data. And then we are providing the anchor values that YOLO v2 traffic uses. And then we're using TCP to set up a connection with the host computer so we can send and receive the data. Here we're processing the bounding blocks using the anchors and the results, and then we can draw the rectangles onto the shapes. We can go into more detail about this if you want to jump onto the Discord. We can talk more about how this got working, or you can wait for the source code in the article to be published later. So I'm going to set this up real quick. Okay. So we're going to get something like this, but we're going to be using live traffic data. So it's not going to be identical. Oh, and if anyone is joining from the start of the stream, we're about to demonstrate YOLO v2 with live traffic data onto the FPGA. And once again, I want to thank the opportunity for Altera in sponsoring this live stream. But this is a pretty cool demo that is going to use live CCTV images and process it in the FPGA. So to set this up, okay, what we're going to do is we're going to run my script. Okay, now we're going to go here and we're going to run the stream. Oh, this needs to be over here. Environmental variables are not shared between okay. Okay. Okay, now we're waiting for an incoming TCP connection. So going to my system, so I'm going to set up the receiver first. And we're going to set up the socket for sending the data. So this data is basically going to grab random traffic data from u.traffic, format it, and send it, the JPEG data, to the system. And let's go ahead and just do 1,000. And what we're going to see here is we're processing the data and we get confidence. Let me go ahead and grab our little image of the traffic. Here's our traffic image. The bounding boxes, the confidence in the bounding boxes probably need to be refined. This is a relatively older YOLO model. But if we use newer YOLO models, did some better pre-processing, tiled the image, you probably could get better results. But here we're taking live traffic data and we're performing some bounding boxes onto the identified cars. The intensity of the green-blue shows the confidence. But there is our demo. That's probably what that's all the new kind of stuff I have set up. We do have a question from YouTube. Can we run the Altera 7? Can we run this on Altera 7 FPGAs? Yes. You can run this AI Suite on the Altera 7 FPGAs. It doesn't provide the same, doesn't provide like the optimized DSPs, but it will function just the same. Okay. We'll let this run a little bit more. Is there any questions? Does anybody want me to potentially dig into more? Of what we're doing here? Yeah, feel free, if you want to look at the Agilex 7, look at my previous videos. Really hard to keep track of all these streams. Okay, so we'll keep that on top, but bring this up. Thanks for joining us for this stream. I'll be doing a stream in the coming weeks. I want to look at more live data over HDMI. There's gonna be a little bit of work of getting the HDMI working on this board and getting it hooked up to the live stream. But I think that would be really interesting. This board has HDMI video. If we can streamline it so that we can have a video input with like an overlay coming out, I think that would be really interesting instead of using UDP, but using a live video feed. And that's probably going to be 2 to 4 weeks, depending upon how difficult it is to get the demonstration up and running. So thank you for joining. I once again want to say thank you to Altera for sponsoring this stream. It was fun to demonstrate some applications that the Agilex 5 has. The Agilex 5 AI optimized DSPs really are a kind of a game changer. You don't really see this functionality across the other Altera FPGAs. And this does help with the DSP processing for the FPGA AI architectures. I know this is a relatively high-level stream. We're running through from low-level demonstrations to high-level demonstrations with real data. I hope that with the source code and articles that you'll be able to dig down more into details and to replicate this with your systems and for your applications. Feel free to like, follow, subscribe, share this video with people who are also using AI and FPGAs or Altera devices. And thank you for watching the stream. I'm probably going to leave this open for a few minutes in case any more questions come up. But that is all the content we have for today. Okay. Drop down and convert viewers. See. Yeah, not like that. Okay. Thank you again, and goodbye.